thanks to Sanjib for giving me the opportunity to present my work in this very nice gathering. Here is the title of my talk, Dynamics of Phase Transitions in Systems Having Velocity Aligning Interactions. So it will be talk essentially on dynamics in active-matter systems, essentially in Wick-Shake matter, Wick-Shake model, Wick-Shake-like model. Okay. And here is the outline of my talk. After the introduction, I will present results from far from steady-state dynamics. As you know, in active-matter systems, instead of approaching towards equilibrium, the systems approach towards steady state. And in that context, basically, I will present results on growth dynamics or so-called phase ordering kinetics. The results will be on domain growth as well as aging phenomena. And in that context, I will present results on finite size scaling and on a particular effect that is also related to kinetics, which is known as Mpemba effect. And then finally, I will present some interesting results, which I find interesting, on transport phenomena at the critical point. So these are kind of pictures, many of them you have seen today. This is a pattern formation in a petri dish by bacteria. There is a giant bird formed by a lot of birds, starlings, and here is a school of fish. Then vorticity, like in you observe in XY model kind of things in a bacterial colony, and similar point-like defects can be seen in hard of shapes and many other places. Okay. So active-matter systems, they do exhibit phase transitions and structures that we know about, that we observe in passive matter systems, but active matter systems are inherently finite. Nevertheless, people do keep interest in learning what would happen if the system size is extended to infinite size limit. And then people are interested in understanding first order transition or the order of transition in general, etc. And here is this famous model that was given by Wick-Shake and co-workers in 1995. And it is about aligning interaction. Basically, given a constituent in the system, a particle in the system, it tries to align its direction along the average direction of motion of its neighbors. That way, some sort of ordering starts developing, and then there is a competition of this ordering or dynamic alignment interaction with some externally imposed noise. And it's like temperature effect in a para-to-ferromagnetic transition. So due to the competition between this noise and the ordering tendency, there emerges a nice order-disorder kind of phase diagram. Okay, so here is the Wick-Shake order parameter, which is the average velocity of the particles of the constituents in the system, and this is the noise strength eta that can take values maximum 2 pi. That gives you all possible directions for generating randomness in the direction of the individual particles. Okay. Now, this model is very good, but there exists no passive interparticle interaction in the system, and that way there is no passive limit for phase transition. That sometimes helps in quantifying the transition, and then also it allows for particle overlap. It's somewhat unrealistic, but we can correct for that with the minimal addition to such model. And here our intention is to actually construct to study the Wick-Shake model, construct a model which is somewhat similar to the Wick-Shake model. And with that model, we want to carry out primarily molecular dynamics simulations. Here, UI is the interparticle potential that we take as Lennard-Jones potential. But the results that I'm going to discuss, they will remain qualitatively invariant even if we take purely repulsive interaction entirely due to Wick-Shake-like this alignment interaction. There can be phase diagrams like this. And then this is the kind of thing in the passive matter context you all know. And in addition to that, we add some activity Fi. Okay. Externally imposed. So basically, this is the average direction of velocity, only the direction, not the magnitude, around a particular particle. And then after each molecular dynamics step, that consists of this part, that is made up of this part, the particle basically tries to align its direction to this average direction with some particular strength Fa. So that way this Fa is something similar to eta, the externally imposed noise. Here of course we have a temperature in the model, that way basically there is inherent noise, and we will choose a particular temperature for which in the passive limit there is no phase separation. Okay? And then you vary this interaction or velocity alignment parameter Fa, and with respect to that, the previous phase diagram that you have seen, that is in terms of the velocity aligning order parameter, and in this system you can see that in addition to the velocity ordering, there exists phase separation in the density field also, and this phase diagram is basically the velocity field phase diagram. So here is the density versus the interaction alignment interaction strength Fa. It's kind of inverted phase diagram like this. There will be a critical point here, and then you prepare your system at a very low value of Fa, so that there is no system is in homogeneous state. So it's a vapor liquid kind of phase transition that is going to happen, single component Lennard Jones with some activity, and then you quench the system from a low Fa to a high Fa. There is going to be a phase separation into vapor and liquid coexisting regions. Okay. So first, the results on domain growth. Here is a typical snapshot. This is the passive limit scenario. If you have favorable temperature, then the passive limit, you start from homogeneously distributed particles, then gradually domains form and it will grow with time, and this is the corresponding active matter scenario. And then you calculate the average sizes of these domains and plot them as a function of time. Typically in statistical mechanics, there is a strong interest since long to understand how the sizes of the domains grow with time. Typically it is power law. So it's a log-log plot. You can see some sort of linear trend, and these are simulation results from finite sizes of systems. So you can see that there is saturation. Okay, but we ask the question whether there is finite size scaling in this. Yeah. And yeah.
Do you see the aligning phase?
So
the flocking phase.
Yes. Okay. Yeah.
No, it was just a curiosity. Sorry.
Okay. Yeah. Okay, so we asked, so in finite size scaling analysis, typically what is done, what is the usefulness of finite size scaling? You exploit the finiteness of the system, the saturation that you see here, to extract the growth exponent in the thermodynamically large system size limit, and in that process you try to, by constructing appropriate scaling formula or form, you try to superimpose data from various different system sizes, and the value of the exponent that gives you the best result in terms of overlapping, that is your exponent. Okay, don't worry too much about these exponent values of 0.88 or 1 or 0.9. The point is that nice. So the first finite size scaling in active matter systems were carried out by Schatte long time back. So this is kind of using the whole time window of the data set, and we find very nice collapse of the data set. And in the following slide, what we do, we try to construct an analytical function, construct in the sense it's empirical, and then you try to fit the collapsed data set with this analytical form, and then you can back transform that thing to describe data from various different system sizes, and it has some practical applications. Okay, now this for the domain growth, it is even before us, people did this, as I mentioned, Schatte did it, and these are the results from aging phenomena that was of significant interest to Shottoda quite some time back in Ising type of systems. So here are the results from two-time relaxation of two-time quantities like the autocorrelation function. And what you see here, there are two times in the argument. One is simply t, other is tw. T is the observation time, and tw is referred to as the waiting time. Okay, and that is also known as the age of the system. So this is basically you have the order parameter, and you take the product of the order parameter values at time t and at time tw, and then ask the question, I want to know how this relaxation is happening. Typically, younger system relaxes faster, so smaller the value of tw, the decay is quicker, and higher the value of TW, you can see that the relaxation or the recovery is happening later. So there is no time translational invariance. So when you plot versus T minus TW, you can see clear separation. Nevertheless, there exists some scaling. Daniel Fisher and David Hughes pointed out that if you plot such quantities as a function of the ratio of T by TW or L by LW, there will be superimposition of data from different TW values. And then this deviation from that overlapping feature is due to the finite size effects. And you can actually carry out similar finite size scaling analysis here as well. You can see nice collapse of data and similar kind of analytical function you can construct, and you can describe each of the system sizes in the similar fashion as in the domain growth. Now, so basically what I want to say that some basic principles or facts of passive matter phase transitions are very nicely obeyed in models of active matter. Okay, now I come to the interesting effect that I mentioned about. This we refer to as Mpemba effect. What you see in this picture, a person in Canada in this particular picture, outside temperature is about minus 30 degrees Celsius. He goes out with a tumbler full of boiling water and throws it into the air, and by the time it reaches the ground, you can see nice crystallites are forming, ice crystals are forming. Okay? And then if you ask the question, if I do the same experiment by using room temperature water, what will happen? The answer to that is, by the time it reaches the ground, within that time scale, this freezing will not occur. So that is Mpemba effect. So these are the you'll see a lot of YouTube videos related to that. And with this Mpemba effect was described even in the works of Aristotle, and it was rediscovered in last century about 60 years back by Erasto Mpemba, a school child then in 6th or 7th standard he was in Tanzania. And since then, statistical physicists have been interested, but the experimental picture has not been that clean. Some people objected by saying that no, Mpemba effect does not exist. And these sort of outdoor experiments, they kind of conclusively say that the effect indeed exists. Okay, nevertheless, and so here is the list of experimental and theoretical works. Just to, I don't probably, I want to go through this. I don't have much time to describe this in details. So this basically, I mean, here I tried to capture the controversial aspects to this effect. Okay, and there are some simulation works, and none of these simulations actually show the existence of the effect. So in this work, what we, again, this particular work I will describe. So one of my former PhD students, he captured this similar curve that Mpemba observed. Okay, you can see, so Mpemba and Osborne at some point they did some controlled experiment, and this is the initial temperature of the water samples, and this is the time to freezing. Okay, and you can see for a large range of initial temperature, the freezing occur quicker for hotter startings. Okay, and yeah, so we needed to follow particular protocol to capture this effect on computers with a particular model which is best suited for ice formation. In any case, that was the definition with respect to water, basic introduction. Now, people have been trying to generalize the effect. You ask the question, say you take a system, not necessarily water, and ask the question, is there any dependence of the relaxation time on initial temperature for reaching the equilibrium corresponding to the quench to a lower temperature? So for any liquid, first it was generalized in the context of liquid, then people started generalizing it in by incorporating spin glasses and many other systems. And recently, so our some other Indian colleagues are also very active. For example, R. Rajesh, Arnav Paul in Math Science in Chennai, and then Prabal Maiti, he didn't probably publish anything yet, but he's also working on that. Maybe some other people also are doing. And the quantum Mpemba effect is also becoming very popular these days. Now, why I quoted these two particular papers, so they considered either spin glass or some combination of ferromagnetic and antiferromagnetic interaction. That way, this water picture that I have described here, so you see after the quench, the systems get stuck in some sort of intermediate metastable states, and the longevity of that metastable states is different for different starting temperatures. Okay, and that's how this delay as you start from lower and lower temperature that occurs, and yeah. And so this sort of models, basically they have inherent frustration in the system that can give rise to metastability, and my understanding was that that was the basic reason why they chose such kind of systems. And now we ask the question simply for ferromagnetic Ising model without any frustration, okay, no impurity, the simple Ising model for which you have in 2D 2.269 Tc, okay, and in 3D 4.51 Tc, etc., nothing other than that. So this is the phase diagram in temperature versus magnetization plane, and you have the critical temperature here. This is a schematic diagram, and we prepare our systems at various different starting temperatures above the critical point, and simultaneously quench each of them inside the critical point and ask what happens, which ones arrive at the new equilibrium quicker than the others. So it's a out of equilibrium phenomena problem, coarsening problem, but it may have connection with equilibrium static critical phenomena, as well as it can have connection with equilibrium or steady state dynamic critical phenomena. Okay. Now, I'm not presenting the results from specifically Ising model. This is a generalized, more generalized version is the Potts model. Okay, and here it is Q equal to 5, and what I'm showing here. So these are the typical evolution snapshots for a particular initial configuration that shows that the one that started from a higher temperature that is getting equilibrated quicker than the other, but it doesn't happen for this particular set of combination of initial configurations. It's a rather general thing. We have calculated various different correlations, probabilities to identify these things. It appears, yes.
You do simulated annealing when you make it?
No, nothing like that. We just allow this.
What is the, anyway, what is the protocol? You do a sudden quench?
Sudden quench.
So that's usually is it first order, right?
Yeah, for Q equal to 5, yeah, it's of course anyway first order transition, but it happens for Q equal to 2, Q equal to across all values of Q. Yeah, it is of course surprising element is there. And so what you see here I have plotted the energy calculated from the expression for the Hamiltonian as a function of time. Okay, and results are there for 3 different starting temperatures, and the results are broken up into 2 subframes. Okay, the upper one contains results from early time, and the lower ones contain results from later time. Okay, and if you look at the upper half, as expected, for hotter starting the energy should be higher. Okay, for lower starting it should be lower, and that's what is happening. But in the bottom frame you can see there is complete trend reversal. Okay, and that means there have been crossings, and that can happen only when the hotter ones show tendency of ordering quicker. Okay, and that's the basic essence of Mpemba effect. The hotter ones are approaching new equilibrium faster than the colder ones. Now we try to generalize it further. Okay, why this Mpemba effect is counterintuitive or surprising? Because so when you start from higher temperature and finally quench all the samples to a lower temperature, basically the thermodynamic distance is higher for higher temperature. Okay, so it's a distance. Okay, the systems further away are arriving at the destination earlier. Now, so if that is
Can it be simply that if you start at hot conditions, you don't have this plenty of small spurious minima at which...
no, that's you're talking about complex energy landscape. I'll come back to that later, or can discuss it during coffee also. So we generalize it in terms of this distance variable. So in our active matter model, it's the FA, the activity strength. which is the tuning parameter, not the temperature. Okay? And this is the phase diagram or the coexistence curve. We prepare outside the coexistence curve along this line, various different FA values. We prepare the initial configurations and simultaneously quench all of them to the same final FA value. Okay? And to remind you, this was the Ising protocol, very similar distance-wise. Okay? And here are the potential energy plots, again, like the Potts model or the Ising model. You can see clear trend reversal. Okay? And don't worry about AM2. AM means active matter. If you study the pure Vic-Shek model, if I call that AM1, there also you see similar features. Okay? Path is instantaneous quench. Path, we do not know which path it is. So with Deepak at some point of time, I had some email exchanges. So we can discuss about it later. So path is, we do not know. We have to identify. These are just instantaneously they are quenched to this point. All of a sudden, you set the value of FA at that value.
What is the energy here?
Energy is the potential energy. Okay, so you have the Lennard-Jones potential plus the activity. Okay, and here we are calculating the potential energy part, and instead you can calculate the average domain size also.
You know, the level of noise is different, no, in the different configurations.
That is true with water also. Whatever.
Because in water, the level of noise is determined by the temperature. Here is determined also by the configuration. No?
Here also you are preparing at, so whatever differences you are, so think of it in terms of distance, okay? You are preparing at various different starting temperatures. In that, in place of that, you are preparing the systems at various different FA values. Okay, you ask the question, if you follow the same distance-related definition.
FA is the strength, but then there is the amplitude. The amplitude depends on the average of the neighborhoods, so it might be, so it's not obvious that it's monotonic, no? Well,
We can discuss that later. So, similar feature you observe here. Okay, so these are the two first things. Now, what I'm going to discuss is the dynamic critical phenomena. Okay, and here is the, so before that, let me recap a bit the static critical phenomena. So here is the standard passive matter phase diagram of a normal chemical system in pressure versus temperature plane. Why I am saying normal? Because if we consider, since at the beginning I discussed about water, for water at the beginning here there will be negative slope. Okay, and various different phases are marked here, and here is my critical point for the vapor liquid coexistence. Beyond that you cannot identify the two phases separately. And so what happens there, if you are below the critical point, significantly below, then there will be a clear-cut interface between the vapor and the liquid phases will appear, and then when you are at a very high temperature above the critical point, you can actually see through the tube. Okay, it's a supercritical vapor phase, and then when you are close to the critical point, there is large length scale fluctuation in the system, basically light scattering at all length scales, and that makes it, this phenomena is referred to as the critical opalescence. Okay, and then in the vicinity of the critical phenomena related to this diverging critical fluctuation, so a lot of interesting things happen for various different thermodynamic properties. In addition to the correlation length diverging with the exponent nu, susceptibility diverges, specificity diverges, the order parameter vanishes with some exponent beta. And you ask the question basically, what are the experimental values of these critical point exponents, and which models can replicate these values, and then you ask questions related to universality, etc. And not only the exponents are universal, the values of the exponents form certain relations. So these are called exponent relation or scaling relations. Some of them are noted here. And then coming to the, so that is static critical phenomena, where you study the thermodynamic quantities, thermodynamic properties. And now let us come to the dynamic critical phenomena or critical dynamics. And so through Van Hove theory, so if the structure factor is written like this, where dt is the thermal diffusivity for a vapor liquid transition that is relevant, And this thermal diffusivity can be written as the ratio of lambda, the thermal conductivity, which is a pure transport property, divided by the isothermal compressibility. Okay? And this KT diverges at the critical point, that's like the susceptibility. And people understood or thought that the singularity in the transport properties will be driven by the singularities in the thermodynamic properties. Okay? So lambda has no critical existence, separate critical existence. Now later, Ian Sengers came up with beautiful experiments. This is a very important picture. So here he plotted lambda for as a function of density, and somewhere here the critical density, you can see nice divergences of the thermal conductivity that shows that the thermal conductivity itself has critical presence. Okay? It shows singular behavior. And then to understand that, Kadanoff in 1960s, he wrote down this generalized Stokes-Einstein relation. So typically the Stokes-Einstein relation, here we call Stokes-Einstein-Sutherland relation. That's because William Sutherland from Australia, he wrote down similar paper a year before Einstein did. Okay? And later Einstein became much more famous, and more recently John Brady in early 2000, he suggested basically everybody to call it Stokes-Einstein-Sutherland relation. So that's what it is. In the single particle context, it is the dS or d single particle equal to kBt over 6 pi eta times A. A is the hydrodynamic diameter of a particle. Okay? Now, Kadanoff said, since it's a large length scale phenomena, let's replace A, the hydrodynamic radius, by the correlation length here. Okay? And then you invoke the critical singularity of eta, and from there actually you can get the critical singularity for the thermal diffusivity, and through that exercise you can actually capture one of those scaling relations like in the static critical phenomena, the exponent relations. Exponents are not all independent. Okay? And then came up this mode coupling theory started by Marshall Fixman, and then various different people made major contributions, Kawasaki, Kadanoff, Swift, and then also came after the this static RG theory, Halperin and Hohenberg came up with the dynamic renormalization group theory. They predicted the values of critical exponents for dynamics. Now, so this is all related to collective transport properties. And what are the collective transport properties? Say shear viscosity, bulk viscosity, these are anyway collective properties of a system, transport properties of a system. Then I spoke about thermal diffusivity. That's not a single particle diffusivity, it's the diffusivity in a sense of the system as a whole. And then you can, for a binary, so, and this discussion was primarily for vapor liquid transition. If you think about phase separation in a binary mixture, then you can introduce something called mutual diffusion constant or interdiffusion constant. How the concentration current when you integrate gives rise to this diffusion constant. That's the system's overall property as a whole. Now, in this slide, I try to show that the single particle transport property, it does not exhibit any singularity. It does not recognize the presence of a critical point. Okay? And everything is happening to the criticality is coming to the collective transport properties. Now, this active matter phase transitions occur due to, various different reasons different from the passive matter. In the passive matter, this interparticle interaction, the passive interaction is very important, okay? Whether you take Lennard-Jones interaction or Ising interaction. But on the other hand, in passive matter, even though we say that the Big-Shake model is like Ising model or XY model, there is no as such passive interaction. Is basically driven by the dynamical alignment and aligning tendency, okay? Like if you are in a fairground, book fair or whatever, I don't know where to go, I see that 5 people are moving in a particular direction, I think that there must be something interesting, so I join them, and by following me and others, several other people join the group. That way some sort of order starts emerging in the system. So we ask the question, can you look at the self-diffusion constant in active matter system, particularly the one I have been considering, and the results will be presented first for the specific model that I have presented so far, but I will, for representative purpose, present the result on Vic-Check model, the pure Vic-Check model also. So here are the plots of self-diffusion constant, which I call micro-diffusion constant or micro-diffusivity, because it's a single particle property. And as a function of Fa, this activity strength, and for various different system sizes, and the peaks that you observe, these are at the locations of the finite size critical points. Okay? As you know that the finite size critical systems have different critical points. In the Ising model, if you study 20, L equal to 20, 100, 500, they will have different critical points. They don't have any, in thermodynamic system sense, there is no meaning, but it gives interesting scaling behavior for approaching towards the infinite limit or thermodynamic limit. And then I find it quite surprising. And so here, if you extract this, the values at the peak, okay, that you plot versus L. That means you're plotting versus the correlation length. At the critical point, the correlation length is of the order of the system size, okay, and that is kind of showing strong divergence. I won't say whether it is because with respect to the Vic-Check model, there still is doubt whether it's a first order transition or a second order transition. Sometimes people feel that the controversy is resolved, and then probably some other people will come up by saying that, okay, that is not true, the problem is not solved yet. But what the statement that I can make, that there is giant enhancement and this is, there is no static counterpart part to it. Okay? And this is from the pure Vic-Check model. You see similar features, and not only that, some sort of point of inflection probably, there are more special points in terms of single particle transport property. So we have to work that out. And why I say it is counterintuitive, number one, here it is the aligning interaction. Okay? And if we go to ABP, active Brownian particle, where diffusion is the primary thing, there you won't see such kind of behavior. And I warn you while reading these pictures, this is, so here in Vic-Check model, what is happening, the system as a whole is moving. Okay? So there is a center of mass motion of the system. You have to subtract the center of mass velocity. That means so a flock of bird is flying in the sky. So you have to sit with the, move along with the birds, and then see what they are doing in between. Okay, so if you calculate that, and that is the standard way to calculate. And so number one, in static critical phenomena, self-diffusivity does not show any such signature. And number two is that collective properties do show, but they vanish. Here, if at all, if I can allow me to safely say, it is diverging, or there is huge enhancement in the value of the micro-diffusivity. And this is, I find it surprising, but we do not have any proper understanding.
Is this diffusivity anisotropic?
You mean the particles are...
So you are in the reference frame of the flow, but you know, can be still anisotropic, no? In several respects, actually.
Probably. But I cannot say for sure now. Yeah. I won't counter you. Yeah. With that, I would like to conclude. But before that, the model that we have used, this is a very small part of the talk or some appendix to it. So this is my first experiment, if you would like to say. So in JNC, in my institution, there is a very dirty lake.
Yes, sir.
Okay. And a lot of fish inside. And the picture is digitally cleaned. Okay? And you can see the all the fish, and then we calculate the so there in the while taking the picture, there are a lot of problems, aspect ratio, this, that, but it tells conveys a picture. So we we calculate the 2-point equal time correlation function, that is this purple symbols. Okay? And then calculate the correlation function from our model. Okay? And they kind of nicely agree with each other. for those who worked with the Ising model, they might, in bare eye, they might think that it's very similar to Ising model. But Ising model, with conserved dynamics, it doesn't describe the picture. Okay? And yeah, with that, I would like to thank you for your attention.
Any questions?
Black ones. So after digitizing, so the black ones are the original ones. Then you do a little bit of coarse grading. There is a lot of noise in the system.
So fish, each black one is black dot is a fish, and
Yeah,
the
black
cross
dots are-
is
yeah, fish.
and the cross ones.
Red ones after removing the noise in the system. So often
Yes,
to identify the domains appropriately, people do such coarse grading exercise.
Can I ask another question? So in the Mpemba effect, so any nonlinear relaxation time would be called a Mpemba effect. Non-monotonic, yes. Is that Mpemba? But then non-monotonic relation with
See,
temperature.
a direct measure is how long it is taking a
True,
system
but that
starting
is a
from.
relaxation time.
Yeah.
So this is a non-linear relaxation. That's what you are looking for. But there is no guarantee, like there is no demand that the relaxation time has to be monotonic. So I don't see
That is true. So here the results that have shown that is from the crossing times, right? I'm showing the crossings and I'm claiming that this is equilibrating faster than the other. Okay, that's how I'm saying that there is Mpemba effect. But this student Sohini Chatterjee, she worked out the total relaxation time and compared even for Ising model. That shows this water-like this thing. But there are various different measures, too many of them these days. Yeah.
Any other questions? Okay, if not, let's thank Subir for the talk. Next speaker is Pinaki from IMSC, Chennai.